Okay, so we're going to try to find the slope and displacement at point B. Now, we could work this problem with direct integration like we've done previously, and it would be a fair amount of work. But when the question is asking for the displacement and slope at a particular point, conjugate beam might be a better alternative. But you'll recall that when you construct the conjugate beam and you find the shear force and moment in the conjugate beam, you do find the slope and displacement in the real beam. So it would be a simpler approach. Also, since it's just a point load, the moment diagram is going to be fairly easy to handle. So the resulting loading on the conjugate beam won't be too bad. So our solution process will be first to build the moment diagram for this. I think what I'll do to cut a little time off is I'll go ahead and tell you, I think you could figure this out yourself, that the shear force at A is 5 kips and the bending moment at A is negative 75 kip feet. And that would simply just require us to make assumptions for the directions of the shear force and bending moment at A and use equilibrium to solve for those. I think you can see that if you just sum forces vertically, there's only one force down 5 kips, so the reaction has to be up 5. The moment at the fixed connection just has to balance the moment about A from the applied force, which is 5 times 15. That's how I got to 75. And just in the opposite direction. If you're not sure about that, then just go ahead and draw the free body diagram and write the equations. You'll get those values. So let's go ahead and draw the shear force and bending moment diagram. So just to remind you, unlike our first exposure to shear force and bending moment diagrams, when we do this, we're only about maybe half to a third of the way through the problem. So this becomes kind of a fundamental component of our work moving forward. So we can start off, you can see I have a shear force of 5. And of course, following our rules, we know that the change in shear is the area in the load diagram. There is no area, so it's going to be unchanged. And then it matches the shear there. So that's our shear diagram. The moment diagram, I'll draw a positive X, indicate positive moment. This will have units of kip feet. I left off the unit for the shear. We're going to start off with a negative 75 as the moment. And of course, the change in moment between the 2 points is the area of the shear diagram. And you can see this is a positive area. It's a rectangle, base times height, 15 times 5 is 75. So if you take negative 75 and add 75, you get 0. And of course, the slope of the moment diagram is equal to the shear, and the shear is constant, and it's positive. So there is my moment diagram. Any questions about that? I think on the first exam, if I'd given you this problem, you've been very happy. So let's construct the conjugate beam. Remember, the first step is in the conjugate beam, is to define reactions and supports that model slope and displacement. So we've already talked about this before, but a fixed connection in conjugate space is what? A free end, and a free end is fixed. So it looks like the beam kind of turns around. Now that's just kind of a coincidence here. It's not a pattern that you should pick up. Okay. Now remember, on the conjugate beam, we're going to apply the moment divided by EI as load. So what I like to do, just to make it easier, is just take the moment diagram as given and just draw it onto the beam. So that'll be over the first 15 feet, and then we have the second 15 feet. Now, let's decide on what this value will be. So this bending moment is what? Positive or negative? Negative. And negative load is down or up?
Down.
It's down. So the load actually looks something like this. And what's the intensity? It's going to be the moment, 75, divided by EI. And just remember, our units are kip feet in the numerator. So I'm looking at this as kind of step one, you draw the moment diagram. Step two, you create the conjugate beam and apply the moment divided by EI as load. And if you've done that correctly up to this point, all you now is you just have a new problem. And this problem is the one we want to find what? Well, the problem statement said at point B, I want to find the slope and displacement. So in the conjugate beam, slope and displacement is shear and moment. So you'll see that in this particular case, at B, I will draw positive bending moment. And positive shear force. You see that? All I have to do is solve for those. How do I do that? Just write the equations of equilibrium for this structure. So to make it a little easier on myself, I'm going to come in here and turn this distributed force into a concentrated equivalent. What would be the value of that force? It's the area of the triangle, which is 1/2 base, which is 15, times height, which is 75. So that's 1/2 the base, 15 feet, times the height, which is 75 kip feet over EI. What was that again, Mr. Rippey?
2,250.
Really?
563.5.
You got to divide by 2.
Oh, sorry. I had
So what 500? 562.5? So that's going to be kip feet and feet again, so that's going to be kip feet squared over EI. And what's the distance from the cut in?
15 plus 12.
Yeah, so I've got 15 feet to here. What's this distance? 2/3 of 15 and 2/3 of 15 is 10. So it'll be a total of 25. So that's everything I need. So to solve this problem now, I'll just go ahead and apply my equilibrium. So I'm going to sum moments at B. Make sure I'm in equilibrium. I'm going to use right-hand rule for my sign convention. So what is this moment with my sign convention? Positive or negative? Positive. And about B, this force creates positive or negative moment? Positive. So I'll have a force of 562.5 kip feet squared divided by EI times its moment arm, which is 25 feet. So what is the moment at B? It looks to be negative, and whatever that times 25 is. $14,000. 14,000. What did you say, Mr. Long? 62. And that will be kip feet cubed over EI. Now remember, moment matches or maps to what in the real beam? Displacement. So it says the displacement is negative. Does it make sense that point B would go down?
Yes.
It does. So I think the sign is right. Now to actually get the value, I would say the displacement at B, which really comes from the moment at B in the conjugate beam, would be this value, negative 14,062.5 kip feet cubed. And now we're just going to have to do some unit conversion. So first, I'm going to divide by EI. E is going to be 30,000 kips per inch squared. I is 800 inches to the fourth. So I got to convert this cubic feet. So I have 1728 inches cubed in a foot cubed. So you can see that my cubic feet cancel, my kips cancel. I have inches to the fifth divided by inches to the fourth, which is just inches. So what's that equal to? 1.01. That's close enough. Everybody else get that? So basically about 1 inch down. What if I told you that that's too much displacement? I only want that displacement to be half an inch. What do I do? Do I rework the problem? No, the only things I can change are E and I. Probably can't go and find a material twice as strong as steel, but I might be able to design a section that has twice the moment of inertia. So that's how you could use this as a design tool if your displacement was restricted. And in most design applications, displacements are restricted. So even though you might check your section, it's not going to have a problem with stress, it's not going to have a problem with strain, is it going to have a problem with displacement? If it does, then you have to go back and read something. Okay, to finish this problem, let's sum forces in the y direction, set that equal to 0. So back to my free body diagram, I have the shear at B acting down, and I have the force also acting down, 562.5 kip feet squared over EI. So what is the shear at B? Negative 562.5 kip feet squared over EI. Now what is shear in the conjugate beam? How does that map back to the real beam?
Slope.
The slope. It says the slope is negative. Does that make sense?
Yes.
So remember, we've already think that our beam is going to deflect like that. So you can see that I have negative displacement and also negative slope. So that seems to match too. So therefore the slope at B is really given by the shear at B, which is this value, negative 562.5 kip feet squared. And now we need to convert that. We still have to divide it by E and I. So again, E is 30,000 kips per inch squared. I is 800 inches to the fourth. And now I have to convert square feet. So that'd be 12 squared. So there's 144 square inches in a square foot. So let's see what my units do. I got kips cancel kips, feet squared, feet squared. I've got inches to the fourth divided by inches to the fourth. I have no unit. This is dimensionless. So this is going to come out. Remember, this is a slope. So this dimensionless number will be in radians. So what is that equal to? It's going to be pretty small, I guess. 0.0033? 34? And that would be in radians. Pretty small angle. Oh, almost ran out of paper there. There it is. You guys see that? So that's a very doable problem. We did that in about 15 minutes, taking our time, talking a lot about it. So I think it's a good problem. Don't you? Let's work another one. What do you think? Any other questions before I stop this one?
Whenever you found displacement, you ask, what if you only want to go half an inch? If you set like a half an inch, what's that equation? You'll say 800 is X.
We could do that.